Imagine you have a big toy box full of many pieces, but some pieces are exactly the same. If you keep all the duplicates, the box becomes heavy and messy. DFA minimization is the same idea. We take a deterministic finite automaton, a machine that decides whether a string belongs to a language, and throw away states that do the same job. The need for minimization is twofold. It makes the machine faster, less work to do for each input letter, and smaller, easier to store, understand, and compare with other machines. Just like a classroom with two chairs that always move together, we can merge them into one chair and still have the same learning experience. Two states P and Q of a DFA are called equivalent if no matter what word W you feed to the machine, after being in P or Q the answer accept or reject is the same. Formally let delta be the transition function, and F the set of accepting states, then P is equivalent to Q if and only if for all W in sigma star the following holds. Delta star of P and W is in F if and only if delta star of Q and W is in F. In plain words, you start in P or Q, read any possible continuation W, and you end up in an accepting state in exactly the same cases. If this holds, P and Q can be glued together because the machine cannot tell them apart. A child-friendly picture. Think of two doors that lead to the same garden. No matter which path you take afterward, they are essentially the same door. The Myhill-Narrowed theorem tells us when a language can be described by a deterministic finite automaton, and how many states the smallest deterministic finite automaton must have. It says, take the relation U tilde V if for every continuation X, the word U followed by X is in the language exactly when V followed by X is in the language. This relation is an equivalence relation, and each equivalence class corresponds to a unique state in the minimal deterministic finite automaton. The number of different classes equals the minimum number of states needed. In simple terms, it is like sorting all possible words into groups where words in the same group behave identically when you add more letters. Each group becomes one room in the smallest possible house that still lets you decide membership correctly. Hopcroft algorithm is a fast way to find those groups, equivalence classes. It starts with two big rooms, the accepting states and the non-accepting states. Then it repeatedly refines the rooms by looking at one letter at a time. If a room contains states that after reading the same letter go to different rooms, we split the original room into smaller ones. The clever part is that Hopcroft always picks the smallest room to split, which guarantees the total work stays low at most big O of sigma size times n log, n where n is the number of original states and sigma the alphabet. Think of it like sorting a pile of colored beads. First you separate red from non-red, then you keep taking the smallest pile and separate it by shade until every pile contains beads of exactly the same shade. The algorithm finishes when no more splitting is possible. The table filling or pair marking method is a more visual way to see which states are different. Create a triangular table listing every unordered pair of states P, Q. First, mark all pairs where one state is accepting and the other is not. They are obviously different. Then repeatedly scan the table. If for some letter O the pair delta of PA, delta of Q is already marked, then P, Q must also be marked because they lead to different futures. When no new marks appear, the unmarked pairs are equivalent and can be merged. An analogy: you have a list of kids and you want to know which kids have exactly the same favorite game. If you already know that Alice and Bob like different games, you write across. Later you discover that Carol always copies the game choice of whoever she talks to. If Carol copies Alice's choice, then Carol cannot be in the same group as Bob. You keep filling the table until you cannot add new disagreements. The method runs in big O of n squared times sigma time, which is simple but slower than Hopcroft for large machines. After we have the equivalence classes, the groups of states that behave the same, we build the minimized DFA as follows. Each class becomes a single new state C. The start state is the class that contains the original start state Q0. A class C is accepting if and only if any, and therefore all original states in C were accepting. For each letter O in each class C, define the transition delta prime of C equals delta of PA. Where P is any state in C, the result does not depend on the choice because all states in C are equivalent. In everyday language, you are taking several identical rooms in a house, painting them the same color, and then connecting the doors exactly as before, but now you have far fewer rooms. The new DFA accepts exactly the same language as the original, because we never changed the way words travel through the machine. We only merged indistinguishable steps. Complexity matters because we often minimize very large automata. Think of pattern-matching engines or lexical analyzers. Table filling uses big O of n squared memory to store the table of pairs and big O of n squared times sigma time to fill it. For a machine with 10,000 states, this quickly becomes impractical, 100 million entries. Hopcroft's algorithm needs only big O of n memory for the partition data structures and runs in big O of sigma times n log n time, which is close to optimal. The log factor comes from repeatedly splitting the smallest block. There are also linear time algorithms for special cases. For example, when the DFA is already a tree, but Hopcroft is the general-purpose champion. In simple terms, table filling is like writing every possible pair of kids on a sheet of paper. It uses a lot of paper. Hopcroft is like using a smart sorting machine that only keeps a few piles at a time, saving both paper and time. Both algorithms guarantee that the resulting DFA has the minimum possible number of states, which is the unique smallest machine for the language. Explanation: let us minimize a concrete DFA. Suppose sigma equals a comma b and the DFA has states q0, q1, q2, q3, q4 with start state q0 and accepting states q3 and q4. The transition function is given by from q0 on a goes to q1 on b goes to q2, from q1 on a goes to q3 on b goes to q4, from q2 on a goes to q3 on b goes to q4, from q3 on a goes to q3 on b goes to q3, from q4 on a goes to q4 on b goes to q4. Step 1. Initialize partition. P equals the set containing the block with q3 and q4 and the block with q0, q1, and q2. The first block are the accepting states, the second block are the non-accepting states. Step 2. Hopcroft refinement. Choose the smaller block containing q3 and q4 as a splitter. For the input the inverse delta of the splitter equals the set q1, q2 because from q1 and q2 leads to q3 or q4. Split the non-accepting block into q1, q2, and q0. For the input b, the same splitter also hits q1, q2, so no new split. Now the blocks are q3, q4, q1, q2, and q0. Using q1, q2 as a splitter does not cause further splits because both go to the same accepting block on both A and B. Thus, the final partition consists of 3 blocks. Step 3. Build the minimized DFA. The new states are A representing the block q3, q4, B representing q1, q2, and C representing q0. The start state is C. The accepting states are because it contains q3 and q4. The transitions are delta prime of C on A goes to B because q0 on A goes to q1 which is in B. Delta prime of C on B goes to B because q0 on B goes to q2 which is in B. Delta prime of B on A goes to A because q1 or q2 on A go to q3 or q4 which are in A. Delta prime of B on B goes to A because q1 or q2 on B go to q4 which is in A. And delta prime of A on A and on B both stay in A, making a sync. The minimized DFA has only 3 states instead of 5, yet it decides exactly the same language. All strings that contain at least one O or one B followed by any number of symbols, ending in the all O or all B sync. Mathematically, the equivalence classes are: the class of q0 is q0, the class of q1 equals the class of q2 which is q1, q2, the class of q3 equals the class of q4 which is q3, q4. Thus we have illustrated the whole pipeline. Define equivalence, refine partitions, and rebuild the smallest DFA.